Thank you for coming. My English is not good, and this is my first speech in English, so I am very nervous, but I will try my best. Okay, let's talk. I will talk about a new attack technique about binary exploitation. File structures in C program are usually created by a call to fopen, which returns a pointer to one of these objects. It identifies a string and contains the information about the file which you want to open. File structure exploitation is one of the common ways to gain control over execution flow. However, to fight against prevalent cyber threat, more and more protection is added to operating system and Glibc, such as DEP, ASLR, and vTable protection. Today, I will show you how to use file structure to bypass the protection and launch remote code execution in a modern operating system. Okay. Hi, I am Angelboy, come from Taiwan. I am a CTF player in 217 and HITBGSEC CTF team, and a researcher in binary exploitation. We often join a lot of CTF such as HITBGSEC, and we got third place this year. I'm a member of GNU. It's an old security group in Taiwan. We also hold HITBGSEC, the largest security conference in Taiwan. I'm also the organizer of vulnerabilities.tw. It's the working site for hackers to test and develop their binary exploitation skill. We can learn many tricks of binary exploitation on this site. Welcome to enjoy our challenges. Here is my agenda today. First, we will introduce what is a file string and what is file structure. Next, we will use a simple case to show you how to use file structure to exploit an EF binary on Linux platform. Moreover, we will explore the methodology to utilize different file structure for attack, which we call file string-oriented programming. Finally, we will introduce a new protection in Glibc and then demonstrate how to make file structure great again. By the way, in this talk, we will focus on Linux and EF binary. At the end, we will talk about some more detail about file on Windows. Okay, let's talk about what is a file string. What happens when we use a raw I/O function in a C program? While we call read or write on a file, kernel will not read or write the file directly. Instead, kernel will handle a kernel buffer and read a lot of data in a file to the buffer. Then it will be copied to your destination address in user space as you want to read or write. The purpose is to reduce the number of hard disk read-write. It will increase the performance in the file operation. After that, Glibc also added a similar mechanism called file string. So what is file string? It's a high-level interface on the primitive file descriptor facility. In its most common form, a string is a logical interface to a file. As C defines the term file, it can refer to a disk file, the screen, the keyboard, a port, file on tab, and so on. It has string buffering mechanism. Characters that are written to a string are normally accumulated and transmitted sequentially to the file in a block. Instead of applying appearing as soon as they are output by the application program. It is portable and high performance. And then what is the word file in all uppercase? It is a string descriptor. A descriptor is linked to a file using a fopen operation. A string is disassociated from a file using a fclose operations. After adding the string buffering mechanism, the architecture diagram is as follows. So, when we use fread or fwrite to read or write a file, it will create a buffer in the user space. Just like system call open and write, it will read a lot of data from kernel buffer to string buffer. Then data will be copied to your destination as you want to read or write. The goal is to reduce the number of system call. In the other word, it will reduce the number of time system trip to kernel. Next, let's take a look over the file structure. File structure is a very complex structure. There are many elements in the structure. Because we don't have much time, so I will not introduce every element in this session. Thus, I will explain a little element which are very important for file structure exploit, such as flags, string buffer, file descriptor, and a virtual function table. The flag in the file structure is used to recall the attribute of the file string, such as read-only, append, and so on. Meanwhile, it also shows the status of the file buffering. Next part is string buffer. It can be divided into three parts: read buffer, write buffer, and the reserve buffer. Read buffer and write buffer, just like their name, is for read or write. If read buffer or write buffer is not created, it will use reserve buffer. Next element is file. File NO, just a file descriptor from the file which you open. It returns from a system call open. Next is file plus. File plus is an extension of file structure. It adds a virtual function table, but file does not have. In a recent Glibc version, file string uses the file plus structure. Standard in, standard out, and standard error also using file plus structure. For all file operations are so readable. If you want to read data from file, it will call a virtual function instead of direct call into system function. That is used for overriding. Because there are different usage depending on the attribute such as Y character. Especially, every file structure is associated with a linked list. The head of the linked list is called IO list O, and the next pointer is called chain. Okay, these are the elements we must know in the file structure exploitation. Next, I will use a few common functions in the file string to show you how the file string works. The first one is fopen. Actually, every function in a file string is very complex. So I pick a few key points here. The left part is the workflow fopen, and right part is the Glibc original function. Let's look at it step by step. First of all, Glibc will allocate a memory space for file structure when you call fopen. Then it will initialize elements in the file structure, such as flags and the virtual function table. It's very like the constructor in the C++ object. Next, it will insert the file structure into the linked list of file string. Eventually, it will call system call open and then fill in the file NO. Next one is fread. From here on, it will start using virtual function for file operations. At the beginning of fread, if the string buffer is not created, we call it null. It will use the function file_do_allocate to allocate a new buffer for file string. By the way, file_do_allocate will use malloc, map, or U-defined memory allocator to allocate the string buffer. After that, fread will use system call to read a lot of data from file to the string buffer. Then copy data which you want to read from string buffer to destination. Okay, that is fread. Next is fwrite. Fwrite is very similar to fread, but the function is opposite to each other. First, it also allocates a string buffer if it is null. Then copy user data to the string buffer from source, and then write data from string buffer to the file only if the string buffer is fill or flush the string. The operation looks like catch. The last one is fclose. It is the opposite of fopen. First is delete the structure from the linked list of file string. Then flush the string. Make sure everything is written to file. Finally, close the file and release the memory space. Okay, the above are the main workflow of some basic function in a file string. Next part is exploit part. I will tell you how to use the file structure to exploit a binary. There are many good targets in file structure. The best one is virtual function table. If we can control the V table, then we can control the flow. Let's use a simple case to explain how to control the flow with file structure. It is a buffer overflow vulnerability in our sample code. It does not check length of user input, so that we can override the file pointer. In the beginning, the program is shown in the picture. The file pointer points to a normal file structure. As soon as the address of buffer contain our input is at 0x6009A0, we override the file pointer with buffer address. In theory, if the program counter equals to fclose will take the buffer as file pointer, and we will control the flow. However, when we run it, we find that it does not crash at call instruction, but a compare instruction, and the crash value is controllable. So why? Let's debug it with glibc source code to see what happened in fclose. We find a segmentation fault at IO acquire lock. It is a function to get lock in file structure. It is the lock structure pointer in file structure, which should be point to a writable memory. It is used to prevent race condition in multi-thread environment and very common in string-related function. As a consequence, if we want to override vtable to gain control, we also have to construct it. But we just need to let it point to a writable and empty memory. So we use a global buffer in BS station as our lock and reconstruct our payload. So that point could point to the global buffer. Because global buffer is initialized with RELRO at the beginning of the program. In the end, our payload will look like as the diagram in this slide. RELRO XAA is the offset of lock. We can use debug or source code in glibc to get the offset. And we also need to paste into 0x100 to override file point. After modify our payload, we run it again. We find we crash at call instruction, and the value of register is our input. That is, we control the program counter. Another interesting, standard in, standard out, and standard error are also a file structure in glibc. Therefore, we can override the global variable if you have base address of glibc. When the program uses some string-related function, it will use it as file pointer and we can control the flow. The above is the basic usage of exploit of file structure. Okay, let's talk about some advanced exploitation. The first one is file string-oriented programming. File string-oriented programming, called FSOP, use file structure to do oriented programming. It's like return-oriented programming, call-oriented programming, and so on. ROP drives the control flow by gauges that all end in a return instruction. COP uses call instruction, and FSOP uses virtual function table with call in a file structure. If we want to do file string-oriented programming, we need to control the linked list of file string and find a powerful function that will call virtual function again and again. It has a powerful function called IO flush or lock. In somewhere we can easily trigger. As a result, churn, which is the next pointer in file structure, and IO list O, which is the head of linked list, both become very important. If we can control these 2 points, then we can control the flow over and over again. So what is IO flag or lock used for? It used to flush all file stream in a linked list at the end of program or program terminate. For example, it will be called when glibc abort, exit, and execute main return. At the first, the goal of IO flush or lock is to prevent all data from being returned to the file when the program enters. In this session, we will take glibc abort routine as our example. When the glibc detects some memory corruption problem, it will enter to the abort routine. The right diagram in the slide is a workflow of glibc abort. In glibc abort routine, it will print some error message, then check file stream if need to flush and call virtual function in the file structure. After do that, it will call exit system call to terminate the program. We simplify the source code of IO flush or lock. We can see the iterator FP is assigned IO list O. The condition is to check the file stream if need to flush. So if the condition is satisfied, it will call function in the V table. Then assign FP to next file structure in the linked list. It will repeat until next point is null. That is, we can construct the linked list to do oriented programming, because we can control everything in the file structure. Let us explain with a simple diagram. At first, IO list O is point to a normal file structure. If you do not use fopen, it usually point to a standard out structure. When memory corruption happens, we can override it with our buffer address, which we can control. And then trigger abort or exit. It will try to flush all file stream in the linked list. As shown in the diagram, if the condition is satisfied, it will call FO function in our fake V table. The parameter of the function is this pointer which points to itself. In this case, if we put a string bar at the beginning of a file structure, it will call FO bar. It is the same as virtual function call in C++. After call FO bar, the control flow will drive to process next file stream, and then call next virtual function. Finally, it will call system bin.sh in this case. We will get the shell, but by the way, sometimes we cannot get shell directly, or we need to do more things. So we need to do oriented programming. It will become very powerful. The result will look like the screenshot shown here. We get the abort message. As well as a shell. Generally speaking, people always think the program is already terminated with this screen. Actually, we get shell. That is so fun, isn't it? It comes from a challenge at HITBGSEC CTF qualification 2 years ago, called House of Orange. Next part is vtable verification. Unfortunately, because more and more attacks use virtual function table to do controller flow, there is a protection added to virtual function table in latest Glibc since last year. It will check the address of vtable before all virtual function call. If vtable is invalid, it will abort, just like the screenshot. Okay, let's see the verification with source code. We can find the check is that vtable must be in Glibc IO vtable session. If it's not in IO vtable session, it will check if the vtable permit virtual function call. There are two checks. The first one is to check if it is for compatibility. And the second one is to check if it for shared library from DOpen. Neither of them will terminate the program. So can we bypass it? Can we bypass it by override the value of IO accept for vtable? It is very difficult because of the pointer guard. Pointer guard is very similar to state guard that is generated at the beginning of the program, and we cannot predict it. It will execution over with pointer when we want to use it. So the method is impossible. Okay, can we bypass it by override the value of the open hook? If the value is not null, it will bypass the check. It sounds good, but if you can control the value, you can also control other good targets, such as malloc hook, free hook, relocate hook, and so on. Accordingly, direct bypass the vtable verification is very hard. So exploitation of file structure is dead. Actually, it's not. Let's make file structure great again. How about change the target from vtable to other element? Can we use other element to do file structure exploitation? The answer is yes. We found two interesting elements, string buffer and a file descriptor in the file structure. After reading Glibc source code, we find if we can override file structure and use fread, fwrite, or other string related function with file structure, we can do arbitrary memory reading or arbitrary memory writing. To simplify the workflow, we will use fread and fwrite as our example. In fact, other string related function can also do it. Okay, let's talk about fwrite. This part, I will use some Glibc source code to explain. Under normal usage, fwrite is used to write data to file. Our goal is to write data in memory to standard out. If we want to do that, we must meet this condition above. First one, set the file descriptor in the file structure to standard out. It also can be set to socket if it is a network program. Second, set flag value is currently putting, and not IO no write. Third, set the write base and the write PTR to memory address from which you want to read. In the end, set IO read end equal to IO write base. So why do I have to set this value? In the flag value, we want to write, so we must not need no write flag. In the fwrite source code internal, we can see whether we cannot set IO current putting. It will adjust the string buffer pointer, and it will affect the result we want. Then it will call IO do write. But it just call virtual function, but not call signal code write directly. There are many complex conditions in this function. Let's take a deeper look. We can see that we must set IO read end equal to IO write base. Otherwise, it will also adjust the string buffer and affect our result we want. So we set it to avoid it. Finally, it will call signal code write and write some data in memory we want. This is a simple code to verify it. If we do nothing on file, it's just a program that writes data you will input to file. After modify value of element in the file structure, you can see that it reads your input and then writes some data called secret in memory. Just like write picture, our input is hello, but the final result is print out with secret. That is, we can read any data in memory. In the other world, if we can control all data in file structure, we can use it to bypass ASLR. Okay, let's demo it. Sorry. The source code is same as the slide. And first, we don't modify any value in file structure. It just write your input to the key.txt, to the file key.txt, txt. And we run it. And we input something. Hello world. Sorry. Oh, sorry. Input hello world, and the output is nothing, and the key.txt it's our input, and we modify the value in the file structure. Then we run it again. Okay. The output is secret and our input. That is put the message in the memory. So we can use it to bypass ASLR. Okay, next part is using fread to do arbitrary memory writing. It is very similar to fwrite. We also need to meet this condition above. First, set the file NO to file descriptor of data in. Second, set flags is not IO no read. Third, set read base equal to read PTR. Lastly, set buffer base and buffer end to memory address which you want to write. However, the distinction between buffer base and the buffer end must be bigger than the size of fread. Otherwise, it will allocate a new buffer. We need to prevent from it. Let's take a deeper look again. Why we need to set read base equal to read PTR? If we not set it, the Glibc will think that there is still data in your buffer. That must be written first. And we can not write our data into this destination. The following condition is buffer size must be larger than size of fread. Because you need to let it think that buffer has enough space to put your data. Next, we do not need the flag IO no read because we want to use read to data to memory. If all condition is satisfied, it will call system call read to read our data to our goal. Okay, we also use a simple code to verify it. It just read data from file and put an empty buffer called MSG. After modify value of element and set MSG as our string buffer in the file structure. If you execute it, you can find that it's waiting for your input. That is, fread is reading from standard in but not from file. And then after input some string like the screenshot, it print out your input but not empty string. In the other word, we can do arbitrary memory writing. Okay, let's demo it again. Okay, we don't modify the value in file structure at first. So it just open a file key.txt and read it, then put a empty buffer. Okay, it write an empty string. So we modify the value in file structure. And you can find it waiting our input. So input high HITB and output is high HITB. That is we write something in the message buffer. We write something to message buffer. So that is we can do arbitrary writing. After you can do arbitrary memory reading or writing, you can control the flow easily. You can override some variable contain function pointer. For instance, you can write GOT or hook series, such as malloc hook, free hook, relocate hook, and so on. By the way, if you can not only use fread and fwrite, but also use any IO string related functions, which use file structure such as fget, fput, and so on. So what if there is no any file operation in the program? Actually, we can use standard in, standard out, standard error with B-table partition as our target. This is a very common use of standard IO function, such as put, printf, and scanf in the program. It will use standard in, standard out, or standard error in Glibc. Let's take two scenarios to show you how to use standard in and standard out to exploit a process. The first one, assume we have some memory corruption on heap and use any standard out related function. How can we do to bypass ASLR in full partition? We can use some heap exploit technology to override flag and partial override IO write base. For example, we can use fastbin attack to partially override unsolved bin if we don't have any address. It will allocate a chunk on standard out so that we can override it. It is very similar to House of Roman, but our target is file structure. After do that, if we call some standard out related function, it will print some memory data in Glibc or heap. Because IO write base have been changed to the front of standard out, and it will print the content of standard out structure. There are many interesting values which contain some Glibc address and heap address in standard out. So we can use the technique to bypass ASLR again. The second one is called execution. Assume there are some standard in related function in the program, such as scanf, fget, and so on. Besides, standard in is on buffer. That will make the standard in function look like no string buffer. But in fact, it has a 1 byte buffer called show buffer in the standard in structure internal at first. IO buffer base and IO buffer end is pointing to it, pointing to show buffer. If we have some memory corruption on heap, we can use unsolving attack, which is very common in heap exploitation, to override IO buffer end with a pointer. The pointer called unsolving is behind the standard in structure. Okay, as a result, we create a large standard in buffer in Glibc again. Okay, that is the standard in buffer. Therefore, it will use the large buffer as a string buffer while we call some standard in related function. For instance, if we call scanf %d, it will call read. The first parameter is 0, the second parameter is buffer base, and the third parameter is size of standard in buffer. So we can override the standard in buffer. override GLibc variable use standing buffer. That is, it can override many global variables in GLibc, such as malloc hook. Finally, if you trigger malloc later, you can control the flow again. There are some another bypass verification. If the virtual function uses IO string file structure, it will invoke another virtual function table without vtable verification. So we can use this function and forge another virtual function table. We can control the program counter again. Let's take IO string finish as our example. If we use IO string finish as the virtual function in file structure, which you forge, we can bypass the vtable verification more easy. And then it will call the virtual function pointer in IO string file structure, which we can point to anywhere. Okay. This one is call a function in IO string file structure. The function pointer is here. That is, we can control program counter again. Another virtual function uses string file as above. It is also very powerful. The above is in the case of the Linux platform. How about Windows? File structure in Windows does not have any virtual function table. But it also has string buffer point. So we can corral it to do arbitrary memory reading and writing. Okay, conclusion. File structure is a good target for binary exploitation. We show that it can be used to arbitrary memory read and write, control program counter, and do oriented programming. But I think it can be used to other exploitation techniques such as arbitrary free or unmap and so on. It's also very powerful in some unexploitable case. Okay, let's try to find more and more exploit technique in file structure. Okay, thank you for listening.
Any questions from the floor? No? All right. Thank you very much again. Thanks.